The universe operates impossible factories. They work at the coldest temperatures imaginable, yet they manufacture the hottest objects that exist. You can't see these factories with your naked eye. They're scattered throughout our galaxy right now. Tonight we're discovering how freezing cold creates blazing fire, how invisible giants forge stars throughout our universe. Drop a comment about what amazes you most about the cosmos. If you enjoy these cosmic journeys, consider subscribing. These explorations are meant to be shared. Enormous invisible structures drift through space between the stars. You can't see them because they're completely dark. Scientists call these giant molecular clouds. Think of them as cosmic warehouses filled with star-building materials. Each cloud contains a mind-boggling amount of stuff. We're talking about tens of thousands of times more material than our entire sun. That's enough raw ingredients to construct thousands of individual stars. These giants span distances that dwarf our solar system. A single cloud stretches across regions so vast that light takes centuries to cross from one side to the other. Yet from Earth, we had no idea they existed until recently. Our galaxy contains hundreds of these invisible factories. They're scattered throughout the spiral arms where most star formation happens. Without these massive reservoirs of gas and dust, no new stars could ever form. Inside these clouds, temperatures drop to nearly the coldest possible point in the universe. We're talking about just a few degrees above absolute zero. That's roughly minus 450 degrees Fahrenheit. At these extreme temperatures, something remarkable happens. Gas atoms slow down dramatically, they barely move at all. This creates the perfect environment for gravity to take control. Here's why cold matters so much. Hot gas moves fast and resists being squeezed together. Cold gas moves slowly and can't fight against gravitational attraction. The colder it gets, the easier it becomes for gravity to compress the material. This frigid environment acts like a cosmic refrigerator. It preserves the raw materials and allows them to clump together. Without these freezing temperatures, the gas would be too energetic to collapse and form stars. Something triggers the cloud to start falling in on itself. Its own weight becomes too much to support. Internal pressure can no longer hold up against the relentless pull of gravity. This process is called gravitational collapse. Imagine a massive cosmic avalanche happening in slow motion. Different parts of the cloud begin contracting toward the center. The collapse accelerates as it progresses. Gravity gets stronger as material packs closer together. What started as a gentle inward drift becomes an unstoppable inward rush. Multiple regions within the cloud collapse simultaneously. Each collapsing region will eventually become a star. This explains why stars typically form in groups rather than alone. As the gas collapses, it gets squeezed into smaller and smaller spaces. Density increases dramatically. Material that once filled vast volumes now concentrates into relatively tiny regions. This compression generates heat. The same physics that makes a bicycle pump warm when you use it operates here. Squeeze gas and it heats up. Squeeze it more and it gets hotter. The center of the collapsing cloud heats up fastest. Temperature rises from nearly absolute zero to thousands of degrees. The heating accelerates as collapse continues. Dense knots of material form within the collapsing regions. These knots will become the cores of future stars. Each core represents a race between gravity pulling inward and pressure pushing outward. The core temperature keeps climbing. Eventually it reaches an almost unimaginable threshold, 10 million degrees Celsius. At this point, nuclear fusion begins. Hydrogen atoms start fusing together to form helium. This process releases enormous amounts of energy. The energy creates outward pressure that finally balances gravity's inward pull. A star is born. What started as a cold, dark cloud has created a blazing nuclear furnace. The transformation from freezing gas to burning star represents one of the universe's most dramatic changes. This nuclear ignition marks the end of collapse and the beginning of a star's life. The newborn star will burn steadily for millions or billions of years. Star formation isn't a solo act. Molecular clouds create entire stellar communities at once. One large cloud typically produces hundreds or even thousands of new stars. These stellar siblings form within a relatively short time period. In cosmic terms, they're all born practically together. This creates what astronomers call star clusters. The process resembles a cosmic fireworks display. Once collapse begins in one region, it often triggers collapse in nearby areas. Star formation spreads throughout the cloud like a chain reaction. These newborn star groups stay together initially. They're bound by their mutual gravitational attraction. Over millions of years, they may drift apart and scatter throughout the galaxy. For centuries, astronomers could only guess how stars formed. Then the Hubble Space Telescope changed everything. Its sharp images revealed star formation happening right before our eyes. The Eagle Nebula became one of the most famous examples. Hubble's pictures show towering pillars of gas and dust. These pillars are literally stellar nurseries where new stars emerge. The Orion Nebula provided another stunning view. This stellar factory sits relatively close to Earth. We can observe the entire process from collapse to ignition. These images proved that star formation is an ongoing process. It's not something that happened only in the ancient past. New stars continue forming throughout our galaxy today. Visible light can't penetrate the thick dust inside molecular clouds. This dust blocks our view like fog blocking distant headlights. For decades, the star formation process remained hidden. Infrared telescopes solved this problem. Infrared light passes through dust much more easily than visible light. These instruments reveal what's happening inside the clouds. Warm objects glow in infrared light. Developing stars heat up their surroundings and become visible to infrared detectors. We can watch the temperature rise as stars form. This technology revolutionized our understanding. We discovered that star formation is far more common and active than previously thought. The universe constantly manufactures new stars. Stars don't last forever. Eventually they exhaust their nuclear fuel and die. When massive stars die, they explode and scatter their contents across space. These stellar explosions enrich the surrounding gas with heavy elements. Carbon, oxygen, silicon, iron and other elements spread throughout the galaxy. This material eventually becomes part of new molecular clouds. The next generation of stars forms from this enriched material. They contain the processed remains of previous stellar generations. It's a cosmic recycling system on an enormous scale. This process explains why newer stars contain more heavy elements than older ones. Each stellar generation adds to the galaxy's chemical inventory. Star formation doesn't just create individual stars. It shapes our entire galaxy. The energy from newborn stars carves channels through the surrounding gas and dust. Massive stars live fast and die young. Their explosive deaths create shock waves that can trigger new star formation in nearby clouds. This creates a feedback loop that spreads throughout the galaxy. Over billions of years, this process has shaped our galaxy's structure. The spiral arms we see today have been shaped through cycles of star birth and death. Each generation influences the next. Chemical evolution follows the same pattern. Early stars contained mostly hydrogen and helium. Each subsequent generation added more complex elements to the mix. The elements essential for life came from stars. Carbon for organic molecules, oxygen for water, iron for blood. All these elements formed inside stellar cores. When stars die, they release these elements into space. The material eventually gets incorporated into new molecular clouds. Future star formation includes this enriched material. Some of this stellar material forms planets instead of stars. Rocky planets like Earth contain the processed remains of ancient stars. We are literally made of star stuff. Life depends entirely on this stellar recycling process. Without the heavy elements created by previous stellar generations, complex chemistry couldn't exist. Molecular clouds connect stellar death to biological birth. Space changes the rules of chemistry completely. In much of diffuse space, hydrogen exists as individual atoms most of the time. In molecular clouds, something different happens. The atoms pair up. This pairing creates what scientists call molecular hydrogen. Two hydrogen atoms link together to form a single molecule. We write this as H2. This simple change makes all the difference. Molecular hydrogen behaves very differently from atomic hydrogen. The paired atoms move more slowly, they radiate heat more efficiently. They respond to gravity's pull more readily. This transformation from atoms to molecules marks the beginning of star formation. Without molecular hydrogen, gravity struggles to overcome the gas's natural pressure. The pairing process creates the conditions necessary for stellar birth. How do you observe something completely invisible? Molecular clouds emit no visible light. They're essentially black against space. Yet astronomers map them with remarkable precision. The secret lies in a simple molecule. Carbon monoxide forms naturally inside these clouds. This molecule broadcasts radio signals across space like a cosmic radio station. Radio telescopes detect these signals from vast distances. Each cloud region transmits at a slightly different frequency. Scientists decode these transmissions to map the cloud's shape, density, and motion. Carbon monoxide acts as our guide to the invisible universe. Without this molecular messenger, we would never have discovered the vast star-forming regions that shape our galaxy. Hydrogen atoms rarely pair up by themselves in space. The vacuum is too empty. Collisions between atoms happen too infrequently. Something else must help them connect. Cosmic dust grains solve this problem. These microscopic particles provide meeting places for wandering atoms. Picture them as cosmic dating services for hydrogen atoms. An atom hits a dust grain and sticks to its surface. Another atom arrives and lands nearby. The grain's surface brings them close enough to bond. They form a molecule and float away together. Without these dust grain matchmakers, molecular clouds couldn't exist. The seemingly insignificant dust particles enable the entire star formation process throughout the universe. Molecular clouds aren't uniform blobs of gas. They contain intricate internal structures. Dense regions nest inside less dense areas. It's like a cosmic set of Russian nesting dolls. The cloud center packs material much tighter than the edges. Scientists call the dense center the core. The sparse outer region forms the halo. Between them lie zones of intermediate density. This layered structure determines where stars form. Only the densest cores have enough material concentrated to trigger gravitational collapse. The outer regions remain too diffuse to form stars. Understanding this architecture explains why stars form in specific locations within clouds rather than everywhere at once. Temperature varies dramatically across different cloud regions. The center stays much colder than the edges. This creates cosmic weather patterns on an enormous scale. Core temperatures hover just above absolute zero. Meanwhile, the outer regions can be dozens of degrees warmer. That might not sound like much, but it makes all the difference. Hot regions experience more turbulent gas motion. Cold regions remain relatively calm. These temperature differences drive winds and currents throughout the cloud structure. The temperature gradients act like a cosmic thermostat. They regulate where and when star formation can begin. Only the coldest regions provide suitable conditions for stellar birth. Powerful magnetic fields permeate every molecular cloud. These invisible force fields stretch across the entire galaxy. They thread through the gas like cosmic highways. The magnetic field lines influence how gas moves within the clouds. Gas can slide along the field lines easily, but moving across the field lines requires much more energy. This creates a preferred direction for gas motion. Material tends to flow along the magnetic highways rather than cutting across them. The field lines shape the cloud's overall structure. Magnetic fields also resist gravitational collapse. They provide additional support against gravity's inward pull. This magnetic pressure must be overcome before star formation can proceed. Gas within molecular clouds never stays still. Complex motions churn throughout these structures. Large streams break into smaller eddies. Small eddies spawn even tinier swirls. Scientists call this chaotic motion turbulence. It resembles the swirling patterns you see in fast-flowing rivers, except these cosmic currents span light years instead of meters. Turbulent motion fights against gravitational collapse. The swirling gas resists being compressed into dense knots. This creates an ongoing battle between turbulence and gravity. Eventually, gravity wins in the densest regions, but turbulence helps determine the final size and mass of forming stars. This chaotic motion shapes the stellar population of our galaxy. What kinds of chemistry happen in these cosmic laboratories? The answer would astonish any earthbound chemist. Hundreds of different molecules form in the frigid darkness. Water molecules assemble on dust-grained surfaces. Methanol appears, ammonia develops. Even complex organic compounds like alcohols and sugars form naturally. These molecules interact in vast chemical networks. One reaction triggers another. Products from early reactions become ingredients for later ones. The chemistry cascades through multiple steps. This cosmic chemistry produces raw materials that can contribute to life. Organic molecules formed in stellar nurseries eventually become incorporated into planets and potentially into living organisms. Molecular clouds develop distinct layers with different properties. Each layer contains gas at different densities and temperatures. The structure resembles a three-dimensional onion. The innermost layer holds the coldest, densest material. This core region will eventually form stars. Surrounding layers contain progressively warmer, less dense gas. Each layer reflects a different part of the cloud's history. The cloud's biography is written in its layers. Understanding this layered structure helps astronomers predict where star formation will occur next. The deepest layers provide the raw materials for the next generation of stars. Dense material doesn't spread evenly through molecular clouds. Instead, it concentrates into irregular clumps and knots. These dense regions float within a sea of thinner gas. Scientists call these concentrations clumps. Each clump contains enough material to form one or more stars. The clumps scatter throughout the cloud like islands in a cosmic ocean. The spacing between clumps determines the final arrangement of newborn stars. Closely packed clumps produce tight star clusters. Widely separated clumps create loose stellar associations. This clumpy structure explains why stars form in groups rather than individually. The original distribution of dense material in the cloud shapes the stellar neighborhoods that result. Molecular clouds exhibit the same structural patterns at every size scale. Large features contain smaller versions of themselves. Small features mirror the structure of larger ones. Scientists call this property self-similarity or fractal structure. It's like looking at a coastline. Whether viewed from space or up close, the jagged outline shows similar complexity. This fractal pattern extends from galaxy-wide structures down to individual star-forming cores. The same organizational principles operate at every level. Nature uses the same blueprint repeatedly. Self-similarity suggests that universal physical processes shape cloud structure. Turbulence, gravity, and magnetic fields work together to create these repeating patterns across all scales. Every molecular cloud faces an invisible battle. Gravity pulls inward constantly. Heat pressure and chaotic gas motion push outward relentlessly. For millions of years, these forces balance each other perfectly. Then something tips the scales. Scientists call this moment Jeans instability. It's named after physicist James Jeans, who first described the process. This represents the exact point where gravity wins the cosmic tug of war. Temperature and density determine when this tipping point arrives. Colder gas resists less, denser regions pull harder. When conditions align just right, the balance breaks. The collapse begins slowly at first. Gravity gains strength as material packs closer together. What started as a gentle inward drift becomes an unstoppable avalanche toward stellar birth. Not every part of a molecular cloud can form stars. Only regions with enough material concentrated in one place have sufficient gravitational pull. There's a minimum mass requirement for stellar birth. This threshold depends on the gas temperature and density. Hotter regions need more mass to overcome their internal pressure. Cooler regions can collapse with less material. Scientists can calculate this critical mass precisely. The calculation reveals something remarkable. Under typical cloud conditions, the minimum mass needed equals roughly the mass of our Sun. This explains why most stars have masses similar to our Sun. Regions below this threshold remain stable indefinitely. They lack the gravitational strength to overcome their internal pressure. Only areas that exceed the critical mass can begin the journey toward becoming stars. How long does it take for a gas cloud to collapse into a star? The answer depends entirely on gravity's strength. Stronger gravity means faster collapse. Weaker gravity means slower compression. Scientists call this the free fall time. It's the time required for collapse if only gravity operates. No other forces interfere. Just pure gravitational attraction pulling everything inward. For typical molecular cloud densities, free fall time spans about 1 million years. That sounds like a long time. But in cosmic terms, it's incredibly fast. Stars form much quicker than astronomers originally expected. This rapid timescale explains why we observe star formation happening throughout the galaxy. The process occurs quickly enough that we can witness it in real time across many different regions. Gas temperature creates pressure that fights against gravitational collapse. Hot gas particles move faster. Fast-moving particles collide more frequently and more forcefully. These collisions generate outward pressure. This thermal pressure acts like an internal spring. It pushes against gravity's inward pull. The hotter the gas, the stronger this resistance becomes. Very hot gas can completely prevent star formation. Molecular clouds stay extremely cold specifically to minimize this resistance. The frigid temperatures reduce particle motion dramatically. Slower particles create less pressure. Less pressure means gravity can win more easily. Understanding thermal pressure explains why star formation requires such cold conditions. Even small temperature increases can stop the collapse process completely. Large molecular clouds don't collapse into single massive stars. Instead, they break apart during the collapse process. The fragmentation creates multiple smaller regions that form individual stars. This splitting happens because different parts of the cloud have different densities. Dense regions collapse faster than sparse regions. The cloud stretches and tears as collapse proceeds unevenly. Each fragment becomes a separate star-forming core. The original cloud might split into dozens or hundreds of individual pieces. This explains why stars typically form in clusters rather than alone. Fragmentation determines the final number of stars produced. More fragments mean more individual stars. Fewer fragments result in smaller stellar populations within each star-forming region. Spinning figure skaters pull their arms inward to spin faster. The same physics operates during stellar collapse. As gas contracts, its rotation speed increases dramatically. This principle governs how rotating disks form around newborn stars. Scientists call this conservation of angular momentum. It's one of nature's most fundamental laws. Rotating objects maintain their total spin regardless of size changes. Smaller size means faster rotation. Most molecular clouds rotate slowly initially, but even tiny rotation becomes significant during collapse. As the gas contracts by factors of thousands, rotation speeds up by the same amount. This accelerating rotation eventually flattens the collapsing region into a disk. The disk becomes the birthplace of planets. Conservation of angular momentum connects stellar birth directly to planetary system formation. What prevents every gas cloud from collapsing immediately into a star? Energy balance provides the answer. Gravitational energy pulls material together. Kinetic energy from motion pulls it apart. The balance between them controls collapse. The virial theorem describes this energy relationship mathematically. When gravitational energy exceeds kinetic energy by a factor of 2, collapse can proceed. Until that ratio is reached, the system remains stable. Temperature measurements reveal the kinetic energy of gas particles. Mass measurements determine the gravitational energy. Comparing these values predicts which regions will collapse next. This energy balance acts like a cosmic switch. It determines precisely when and where star formation begins throughout the galaxy. Star formation doesn't end when collapse starts. Material continues falling inward long after the initial compression begins. This ongoing process is called accretion. It steadily adds mass to the developing star. The infalling material forms streams and spirals as it approaches the center. These streams carry additional mass from the surrounding cloud. They feed the growing star like cosmic supply lines. Accretion continues for millions of years after collapse begins. During this time, the star's mass increases steadily. The final stellar mass depends on how much material the accretion process delivers. Understanding accretion explains why stars have such a wide range of masses. Different regions receive different amounts of additional material during their formation process. Why do collapsing gas clouds heat up? The answer lies in energy conversion. Gravitational energy doesn't disappear during collapse. Instead, it transforms into heat energy. The gas warms up as it contracts. This heating process follows the same physics that warms a bicycle pump when you use it. Compression generates heat. The more compression, the more heat produced. Stellar collapse involves extreme compression. Temperature rises fastest in the center where compression is strongest. The core reaches thousands of degrees while outer regions remain cold. This temperature gradient drives complex gas flows. Eventually, the core temperature reaches millions of degrees. At that point, nuclear fusion begins. The collapsing gas cloud has successfully transformed into a burning star. Collapsing gas doesn't fall inward uniformly. Different layers experience different pressures. The center feels the highest pressure. Outer layers experience progressively lower pressure. This creates a stable arrangement. Scientists call this hydrostatic equilibrium. Each layer balances the inward pull of gravity against the outward push of pressure. The balance creates a stable, layered structure during collapse. This pressure gradient prevents runaway collapse. Without it, all the material would rush to the center instantly. The gradient allows controlled, steady compression over long periods. Hydrostatic equilibrium explains why stellar cores develop gradually. The pressure structure regulates the collapse process and determines the final stellar properties. Do all molecular clouds collapse at the same rate? Absolutely not. Initial conditions determine whether collapse happens quickly or slowly. Dense, cold regions collapse rapidly. Sparse, warm regions compress gradually. Temperature makes the biggest difference. Cold clouds overcome pressure resistance easily. Warm clouds struggle against stronger thermal pressure. The temperature difference can change collapse times by millions of years. Turbulent motion also affects collapse speed. Calm regions fall together smoothly. Turbulent regions experience chaotic motions that slow the process. Some regions may never achieve stable collapse. These varying timescales create the diversity we observe in stellar nurseries. Some regions form stars rapidly. Others take much longer. The initial conditions write the script for each collapse story. When massive stars die, they don't fade quietly. They explode with unimaginable violence. These stellar explosions are called supernovas. Each one releases more energy than our sun will produce in its entire lifetime. The explosion creates a shock wave that races outward at thousands of miles per second. This cosmic blast wave slams into nearby molecular clouds like a hurricane hitting a house. The impact compresses the gas dramatically. Compressed gas becomes denser. These changes trigger the gravitational collapse we discussed earlier. What was once a stable cloud suddenly begins forming new stars. The dying star's explosion creates the next generation of stellar birth. Supernova shock waves can trigger star formation across vast regions of space. A single explosion influences cloud collapse over distances spanning hundreds of light years. Death becomes the catalyst for new cosmic life. Hot young stars don't just shine brightly. They also blow powerful winds of charged particles into space. These stellar winds stream outward at incredible speeds. Scientists call this process mass loss because the star literally loses material. Stellar winds push against the surrounding gas like cosmic snowplows. They carve out huge cavities in the molecular clouds. The displaced gas piles up at the edges of these expanding bubbles. These compressed edges become prime locations for new star formation. The wind pressure squeezes the gas beyond its normal density. Gravity takes advantage of this compression to initiate collapse in regions that were previously stable. Multiple hot stars working together can reshape entire molecular clouds. Their combined winds create complex patterns of compression and rarefaction throughout the star-forming region. Our galaxy isn't just a random collection of stars. It has organized spiral arms that sweep through space like cosmic traffic lanes. Molecular clouds must navigate through these crowded galactic highways during their orbital journey. Spiral arms contain higher concentrations of stars, gas, and gravitational forces. When a molecular cloud enters a spiral arm, it encounters increased pressure from all directions. The cloud gets squeezed like a sponge being compressed. This compression happens only during spiral arm passages. Between the arms, clouds drift peacefully through less crowded space. But the spiral arm squeeze provides just enough extra pressure to tip stable clouds toward collapse. The spiral pattern explains why star formation occurs in organized waves across our galaxy. Each spiral arm passage triggers a new burst of stellar birth throughout the affected molecular clouds. Space seems empty, but molecular clouds do occasionally collide with each other. These cosmic crashes happen when clouds traveling in different directions meet. The collision creates spectacular shock zones where gas from both clouds piles up. Before collision, each cloud maintains its own structure and density. After collision, the contact region becomes much denser than either original cloud. This collision zone experiences pressures far beyond normal molecular cloud conditions. High-density shock zones collapse rapidly into new stars. The collision essentially force feeds gravitational collapse by cramming extra material into small spaces. What would have taken much longer can happen far more quickly. These cloud collisions demonstrate how external events can dramatically accelerate star formation. The universe uses cosmic crashes to jump-start stellar birth in regions that might otherwise remain dormant. Newly formed massive stars create their own star-forming environments. These hot young stars emit intense ultraviolet radiation that strips electrons from nearby hydrogen atoms. This creates what astronomers call an HI region, a bubble of ionized gas. The ionized bubble expands rapidly outward from the new star. Hot ionized gas takes up more space than cold neutral gas. The expansion pushes against the surrounding molecular cloud material. Gas gets compressed into dense shells at the edge of the expanding bubble. These shells become the next generation of star-forming sites. The newborn star essentially creates the conditions for its stellar siblings to form. This process can continue for multiple generations. Each new crop of stars creates more expanding bubbles that trigger even more star formation throughout the molecular cloud. Do molecular clouds need outside forces to begin star formation? Not always. Internal turbulence within clouds can create its own compression zones. Chaotic gas motions naturally produce regions of higher and lower density. Turbulent eddies and swirls concentrate material in some locations while dispersing it from others. The concentrated regions can reach densities high enough to trigger gravitational collapse. No external shock wave required. This internal compression explains why isolated molecular clouds can still form stars. The turbulent motion acts like an internal trigger mechanism. Random gas flows occasionally create the right conditions for stellar birth. Turbulence ensures that star formation can begin even in clouds that haven't encountered external disturbances. The chaotic internal motions provide a backup mechanism for initiating cosmic star production. Molecular clouds change as they age. Even without external triggers, their internal structure evolves slowly. Small density variations grow larger over millions of years. Eventually, some regions become gravitationally unstable to their own mass. This process is called gravitational instability. Dense knots within the cloud gradually accumulate more material. As they grow heavier, their gravitational pull increases. The stronger gravity attracts even more material. The growth process accelerates over time. What starts as a tiny density enhancement becomes a massive concentration that can no longer resist its own gravitational pull. Collapse begins from purely internal evolution. Gravitational instability provides a natural timescale for star formation. Even isolated clouds will eventually form stars as their internal density structure evolves beyond the stability threshold. Molecular clouds don't exist in perfect vacuum. They're surrounded by hot tenuous gas that fills the space between stars. This hot gas exerts pressure on the cloud boundaries like atmospheric pressure compressing a balloon. External pressure varies throughout the galaxy. Regions near active star formation contain hotter, denser gas that creates stronger external pressure. Quiet galactic locations have cooler surroundings with weaker pressure. Increased external pressure compresses the entire molecular cloud uniformly. This compression raises the internal density throughout the cloud. Higher density brings regions closer to the threshold for gravitational collapse. External pressure acts like a slow cosmic vise. It gradually squeezes molecular clouds toward the conditions necessary for star formation. Even small pressure increases can tip marginally stable clouds toward stellar birth. Molecular clouds orbit within our galaxy's gravitational field. But this field isn't perfectly uniform. Different parts of the cloud experience slightly different gravitational forces. These variations create tidal effects that stretch and distort cloud structure. Tidal forces work like the moon's effect on Earth's oceans. Gravity varies with distance from the galactic center. The variation pulls clouds into elongated shapes during their orbital journey around the galaxy. Stretching concentrates material along certain directions, while dispersing it along others. The concentrated regions can reach densities sufficient to initiate gravitational collapse. Tidal distortion becomes another trigger mechanism for star formation. Galactic tidal effects provide a gentle but persistent influence on cloud evolution. They slowly reshape molecular clouds and create conditions favorable for stellar birth throughout their galactic orbital cycles. The universe occasionally produces events of almost unimaginable violence. Gamma-ray bursts release more energy in seconds than our sun will produce in billions of years. These cosmic catastrophes occur when the most massive stars collapse into black holes. The energy release can create shock waves that propagate across large regions of the galaxy. Unlike supernova shock waves that affect local areas, gamma-ray burst shock waves may influence molecular clouds across thousands of light years. These extreme shock waves may trigger star formation across multiple molecular cloud complexes. The compression can spread across unusually large regions. Rare events can create widespread consequences. Gamma-ray bursts demonstrate how the universe's most violent phenomena may also stimulate creative processes. Cosmic destruction can become the seed for massive waves of stellar construction. Star formation doesn't happen just once and stop. Each new generation of stars creates conditions that trigger the next generation. This creates a self-sustaining cycle of stellar birth that can continue for millions of years. Newborn massive stars produce stellar winds and eventual supernova explosions. These phenomena compress surrounding gas and trigger new collapse events. The new stars then repeat the process with their own winds and explosions. This feedback mechanism explains why star formation occurs in waves that sweep across galactic regions. Each stellar generation plants the seeds for the next generation. The process becomes self-perpetuating across vast timescales. Understanding this cycle reveals why some galactic regions experience prolonged periods of active star formation while others remain quiet. The presence or absence of triggering feedback determines whether stellar birth continues or ceases. Deep within a collapsing gas cloud, something remarkable begins to form. The very center starts accumulating material faster than anywhere else. A dense core emerges from what was once uniform gas. This marks the first step toward actual star creation. Scientists call this forming object a protostellar core. It's not yet a star. It's not even hot enough to glow. But it contains the concentrated mass that will eventually become a burning stellar furnace. The core grows steadily as more material falls inward. Gravity pulls gas from increasingly larger distances. What started as a tiny dense spot gradually becomes a massive central concentration. This core formation represents the point of no return in stellar birth. Once a dense core establishes itself, the transformation from gas cloud to star becomes inevitable. Collapsing gas rarely falls straight inward. Most molecular clouds rotate slowly. Even tiny rotation becomes significant when the gas contracts. The spinning motion creates something unexpected, a flat disk around the central core. This happens because of physics you can demonstrate with a figure skater. Pull your arms inward and you spin faster. As gas spirals toward the center, it speeds up dramatically. The rapid rotation flattens the material into a thin disk. Scientists call this structure an accretion disk. Material in the disk continues spiraling slowly inward toward the growing protostar. The disk acts like a cosmic conveyor belt feeding mass to the central object. Accretion disks become the birthplaces of planets. The same rotating structure that feeds the growing star also provides the raw materials for planetary system formation. Something seems wrong with this picture. Material falls inward to build the star, but simultaneously, high-speed jets of material blast outward from the same region. These jets shoot away from the poles of the rotating system at incredible speeds. The jets flow in directions perpendicular to the accretion disk. While the disk feeds material inward, the jets carry material away. This seems wasteful. Why would a forming star throw away the very material it needs to grow? Scientists call this process bipolar outflow. The outflow serves an important purpose. It removes excess angular momentum from the system. Without this process, rotation would prevent further collapse. The jets act like cosmic pressure release valves. They allow the accretion process to continue by removing the rotational energy that would otherwise halt stellar growth. Young protostars glow intensely even though they cannot yet burn nuclear fuel. Their cores remain too cool for hydrogen fusion, yet they shine brighter than many fully formed stars. How do they generate so much energy without nuclear reactions? The answer lies in gravitational contraction. As material continues falling onto the protostar, gravitational energy converts to heat. The compression itself generates enormous amounts of energy. This makes the protostar luminous long before fusion begins. Astronomers classify many of these young low-mass objects as T-Tauri stars. They're named after the first example discovered in the constellation Taurus. These stars represent the teenage phase of stellar development. T-Tauri stars remain highly active and variable. They can't yet achieve the stable energy balance that characterizes mature stars. Their brightness fluctuates dramatically as accretion rates change and internal structure adjusts. What happens when those high-speed jets slam into the surrounding gas cloud? They create some of the most beautiful objects in the universe. The collision zones glow brilliantly as shock waves heat the gas to thousands of degrees. Astronomers call these glowing regions Herbig-Haro objects. They're named after the two astronomers who first studied them systematically. These objects look like bright knots and streamers of colorful gas stretching across space. The shock waves move at supersonic speeds through the surrounding medium. They compress and heat the gas they encounter. The heated material radiates energy at specific wavelengths that create the characteristic colors. Herbig-Haro objects provide direct visual evidence of the outflow process during star formation. They make the otherwise invisible jets visible by marking their collision points with the surrounding gas. Before full hydrogen fusion begins, protostars experience a preview of nuclear burning. They start fusing deuterium, heavy hydrogen with an extra neutron. This fusion reaction begins at much lower temperatures than regular hydrogen burning. Deuterium fusion provides a temporary energy source during late protostellar development. The nuclear reactions help stabilize the object's structure, but deuterium is rare. The fuel supply runs out quickly compared to the vast hydrogen reserves. This brief burning phase marks an important transition. The protostar begins to resemble a real star in terms of energy generation, but it's still not quite ready for the main stellar burning that will define its adult life. Understanding deuterium burning helps astronomers identify very young stellar objects. The presence of this reaction indicates a star in the final stages of formation but not yet fully matured. Inside the forming protostar, material doesn't stay still. Hot gas rises toward the surface. Cool gas sinks toward the center. This creates large-scale circulation patterns throughout the interior. Scientists call this process convection. Convective circulation differs dramatically from the structure of mature stars like our Sun. Adult stars have stable layered structures with limited internal mixing. Protostars remain thoroughly mixed by vigorous convective motions. This internal churning affects the protostar's development. Convection transports energy efficiently from core to surface. It also distributes chemical elements uniformly throughout the stellar interior. The convective phase ends as the protostar matures. Eventually, stable layers develop and the vigorous internal circulation calms down. This transition marks another step toward true stellar adulthood. Young protostars possess much stronger magnetic fields than adult stars. These powerful magnetic fields create intense stellar activity. The magnetic field lines twist and snap like cosmic rubber bands. Each snap releases enormous amounts of energy in stellar flares. The magnetic activity generates X-rays and other high-energy radiation. Young stellar objects can produce X-ray flares thousands of times more powerful than anything our Sun creates. This intense radiation affects the surrounding environment dramatically. Strong magnetic fields also help drive the jets and outflows we discussed earlier. The magnetic field lines provide the mechanism for accelerating material to high speeds and focusing it into narrow beams. Magnetic activity gradually decreases as protostars mature. Adult stars like our Sun still have magnetic fields, but they're much weaker than the intense fields of young stellar objects. Eventually, the protostar's core reaches a critical temperature, 10 million degrees Celsius. At this point, hydrogen nuclei move fast enough to overcome their electrical repulsion. Nuclear fusion begins. The protostar becomes a true star. This transition doesn't happen gradually. Fusion ignition is sudden, dramatic. Once it starts, nuclear burning provides enough energy to halt gravitational contraction. The star achieves hydrostatic equilibrium, a stable balance between inward gravity and outward pressure. Scientists call this moment zero-age main sequence arrival. The star joins the main sequence. The stable stellar population that includes our Sun. It will remain on the main sequence for most of its lifetime. The achievement of sustained nuclear fusion marks the end of the formation process. What began as cold gas has become a nuclear furnace that will burn steadily for millions or billions of years. Star formation and planet formation happen simultaneously. The same accretion disk that feeds material to the growing protostar also provides raw materials for planetary construction. Dust particles in the disk begin sticking together to form larger and larger objects. This process starts with microscopic grains. They collide and stick to form pebbles. Pebbles accumulate into boulders. Boulders aggregate into asteroids. Eventually, some objects become large enough to attract additional material gravitationally. The largest objects become planets. Rocky planets form in the inner disk where temperatures vaporize ice. Gas giant planets develop in the cooler outer regions where ice can survive and help build massive cores. Planetary system formation explains why most stars have planets. The same physical processes that create stars naturally produce planetary systems as byproducts of the star formation mechanism. What determines how massive the final star becomes? Two competing processes control the outcome. Accretion adds material to the growing protostar. Mass loss through jets and stellar winds removes material from the system. The balance between these processes determines the star's final mass. High accretion rates with weak outflows produce massive stars. Low accretion rates with strong outflows result in smaller stellar masses. Environmental conditions influence this balance. Dense cloud regions provide more material for accretion. Active stellar neighborhoods create strong radiation fields that can halt accretion prematurely. This mass determination process explains why stars span such a wide range of sizes, from tiny red dwarf stars to massive blue giants. The diversity reflects different outcomes of the accretion versus mass loss competition during formation. Star formation faces constant opposition from within molecular clouds themselves. Chaotic gas motions create turbulent pressure that fights against gravity's inward pull. These random movements add an extra layer of resistance beyond ordinary thermal pressure. Scientists call this phenomenon turbulent pressure. Imagine a crowd of people all moving in different directions at once. The random motions create pressure even when the crowd isn't hot. Gas behaves similarly when turbulent motions churn throughout the cloud. Turbulent pressure can completely prevent star formation in some regions. The chaotic motions make the gas behave as if it's much hotter than its actual temperature. This extra pressure support keeps many cloud regions stable against gravitational collapse. Understanding turbulent pressure explains why not every part of a molecular cloud forms stars. The random internal motions provide an additional barrier that gravity must overcome before stellar birth can proceed. Magnetic fields thread through every molecular cloud like invisible highways. These fields don't just guide gas motion. They actively resist compression of the material. When gas tries to squeeze together, magnetic field lines push back. This resistance occurs because gas in space contains charged particles. Charged particles can't move freely across magnetic field lines. They get trapped and follow the field's direction. This creates what scientists call magnetic pressure. Magnetic pressure works like an additional spring pushing outward against gravitational compression. The stronger the magnetic field, the more resistance it provides against collapse. Very magnetized clouds may never form stars at all. The magnetic field strength varies throughout different cloud regions. Areas with weaker fields collapse more easily. Regions with strong magnetic fields remain stable much longer against gravitational attraction. Most molecular clouds rotate at least slightly. Even tiny rotation becomes a major problem during collapse. As gas contracts, conservation of angular momentum makes it spin faster. Eventually, the spinning motion creates enough outward force to halt collapse completely. This process resembles a figure skater pulling in their arms. The skater spins faster as they contract. But unlike a skater, collapsing gas can spin so fast that centrifugal force overcomes gravity entirely. Scientists call this rotational support. The spinning gas literally supports itself against gravitational collapse through pure rotation. Instead of forming a compact star, the material spreads into a flat rotating disk. Rotational support explains why forming stars often have circumstellar disks. The gas can't collapse directly to the center because rotation prevents it. The material must find alternative pathways that conserve angular momentum during the infall process. Higher gas temperatures make star formation much more difficult. Hot gas moves faster and creates stronger pressure resistance against gravitational compression. This changes the minimum mass needed to trigger collapse. The critical mass threshold is called the thermal Jeans mass. It increases dramatically with temperature. Gas that could easily collapse when cold becomes completely stable when heated by even small amounts. This temperature sensitivity acts like a cosmic thermostat controlling star formation. Small temperature increases can shut down stellar birth across entire cloud regions. Cooling processes must operate effectively to enable continued star production. External heating sources can halt star formation by raising gas temperatures above critical thresholds. Understanding thermal Jeans mass explains why star formation requires such precisely controlled temperature conditions. Cosmic rays and ultraviolet starlight constantly bombard molecular clouds from outside. This high-energy radiation heats the gas above its natural cold temperature. Even small amounts of heating create significant additional pressure that opposes gravitational collapse. The heating process works by transferring energy to gas particles. Faster moving particles create higher pressure. Higher pressure provides stronger resistance against gravitational compression. The heated regions become much more stable against collapse. Scientists call this process ionization heating. The radiation strips electrons from atoms and molecules. The resulting charged particles move faster than neutral atoms. This increases the effective temperature of the gas. Ionization heating represents a fundamental limit on star formation efficiency. Even isolated molecular clouds experience background radiation that prevents the gas from cooling to absolute zero. This limits how dense and cold cloud regions can become. Young protostars create their own star formation problems. The powerful jets they produce actually work against further stellar growth. These jets carry away material that could otherwise add to the star's mass. Bipolar jets remove material from the star-forming region at speeds of hundreds of kilometers per second. This represents a direct loss of potential stellar mass. The jets literally steal material that gravity worked to accumulate. The jets also carry away rotational energy. This solves the angular momentum problem but reduces the efficiency of mass accumulation. Less mass reaches the central protostar because the jets transport it away from the system. Jet activity explains why star formation is inherently inefficient. Most of the original cloud material never becomes part of any star. The outflow process removes it from the star-forming region entirely. Once massive stars ignite nuclear fusion, they begin destroying their own stellar nurseries. These newborn giants produce powerful stellar winds that blow away the remaining gas. The winds prevent other nearby regions from accumulating enough material to form additional stars. Stellar winds from massive stars carry enormous energy. They can clear out entire molecular cloud complexes within a few million years. The dispersal process stops star formation in surrounding areas. This creates a self-limiting cycle in star formation. The first generation of massive stars prevents further stellar birth in their neighborhood. The process naturally regulates the number of stars that can form in any given region. Stellar wind feedback explains why star formation occurs in bursts rather than continuously. Each burst of stellar birth quickly exhausts the local gas supply and prevents immediate follow-up star formation in the same area. Bright stars don't just shine harmlessly. Their intense radiation creates actual physical pressure called radiation pressure. This pressure pushes against dust grains and gas particles like a cosmic wind. Very luminous stars can blow away their surrounding material entirely. Radiation pressure becomes extremely strong around massive hot stars. These stellar giants shine with the power of millions of suns. Their intense light creates pressure forces comparable to hurricane winds on Earth. The pressure particularly affects dust grains in the surrounding gas. Light pushes directly against solid particles. The accelerated dust grains drag gas along with them through collisions. This process can disperse entire cloud regions. Radiation pressure creates a maximum possible stellar mass. Stars cannot grow beyond a certain size because their radiation pressure would blow away any additional material trying to accrete. This natural limit determines the upper boundary of stellar masses. Massive stars heat their immediate surroundings to extreme temperatures. The hot gas expands rapidly and creates large bubbles of empty space. These expanding bubbles sweep away the cold, dense gas needed for continued star formation. Scientists call these structures H2 regions because they contain ionized hydrogen. The hot ionized gas expands much faster than cold molecular gas. It bulldozes through the surrounding material like an expanding explosion. The expanding bubbles can grow to enormous sizes. They stretch across hundreds of light years and displace vast amounts of star-forming material. Eventually, they blow out of the molecular cloud entirely. H2 region expansion represents one of the most effective ways that stars destroy their own formation environments. The process can halt star formation across entire molecular cloud complexes within relatively short timeframes. Individual feedback processes gradually weaken molecular clouds over time. Stellar winds disperse gas. Radiation pressure pushes material away. Expanding bubbles clear out regions. Eventually, these effects combine to destroy the entire star-forming complex. The destruction doesn't happen instantly. Multiple generations of stars contribute their feedback effects. Each generation makes the environment more hostile to further star formation. The cumulative damage eventually overwhelms the cloud's gravitational binding. Scientists call this process molecular cloud dispersal. It represents the natural end point of star formation in any given region. No molecular cloud lasts forever once star formation begins. Cloud dispersal explains why star formation cannot continue indefinitely in the same location. The process contains its own termination mechanism, built into the feedback effects of stellar birth itself. The chemical makeup of gas dramatically affects how easily stars can form. Elements heavier than hydrogen and helium help cool the gas more efficiently. They also form dust grains that aid molecular formation. Regions with different chemical compositions experience vastly different star formation rates. Scientists call heavy elements metals in astronomical terminology. Metal-rich regions cool faster and form more dust. Metal-poor regions struggle to achieve the cold, dense conditions necessary for efficient stellar birth. This creates a cosmic chicken and egg problem. Stars produce heavy elements through nuclear fusion, but heavy elements are needed for efficient star formation. Early cosmic regions had difficulty forming stars because they lacked the heavy elements produced by previous stellar generations. Understanding metallicity effects explains how star formation has evolved throughout cosmic history. Each generation of stars makes the environment more conducive to future stellar birth by enriching the gas with heavy elements. How do hundreds of stars appear together in tight groups across space? The answer lies in the collective nature of stellar birth. Most stars don't form alone. They emerge in massive group births that create what astronomers call star clusters. These stellar nurseries produce anywhere from dozens to thousands of stars within the same molecular cloud complex. The stars form over relatively short time periods. In cosmic terms, they're all born practically simultaneously. Scientists call these stellar families star clusters. Open clusters contain younger stars born from the same molecular cloud. Globular clusters hold ancient stars formed early in galactic history. Both types represent group stellar birth events. Understanding cluster formation reveals why most stars in our galaxy were born with stellar siblings rather than in isolation. The physics of molecular cloud collapse naturally favors group birth over individual stellar formation. Star clusters don't have uniform structure throughout their volume. Instead, they display nested organization like a set of Russian nesting dolls. Small groups of stars cluster together. These small groups combine into larger associations. The larger associations form even bigger structures. This hierarchical arrangement reflects how the original molecular cloud fragmented during collapse. Dense clumps within the cloud became small stellar groups. Groups of clumps formed larger star-forming regions. The overall cloud structure determined the final cluster architecture. Astronomers observe this hierarchy throughout star-forming regions. Binary stars orbit within small multiple star systems. Small groups cluster within larger associations. Associations combine into sprawling stellar complexes spanning hundreds of light years. The hierarchical structure explains why star formation produces such diverse stellar neighborhoods. From tight binary systems to loose associations, the variety reflects different scales of the original cloud fragmentation process. Something remarkable happens as star clusters evolve over time. The heaviest stars gradually migrate toward the cluster center. Lighter stars slowly drift outward toward the edges. This cosmic sorting process occurs purely through gravitational interactions between cluster members. Scientists call this phenomenon mass segregation. It works like cream rising to the top of milk, except gravity pulls heavy stars inward instead of upward. More massive stars have stronger gravitational attraction and tend to capture central positions. The segregation process takes millions of years to complete. Young clusters show mixed populations with stars of all masses scattered throughout. Older clusters display clear separation with massive stars concentrated centrally. Mass segregation creates the dense stellar cores observed in mature star clusters. These cores contain the cluster's most massive and luminous stars packed into relatively small volumes. The concentration makes these regions extremely bright and active. Do stellar nurseries randomly produce stars of all different sizes? Absolutely not. Nature follows a precise statistical recipe for stellar birth. This recipe helps determine how many massive stars, medium stars, and low-mass stars form in every star cluster. Astronomers call this pattern the initial mass function. It describes the probability distribution for stellar masses at birth. The function remains remarkably similar across different star-forming environments throughout our galaxy. The pattern strongly favors low-mass stars over high-mass stars. For every massive blue giant that forms, nature produces hundreds of smaller red dwarf stars. This creates a stellar population dominated numerically by the smallest stars. Understanding the initial mass function helps astronomers predict cluster properties. By counting the most massive stars, they can estimate the total number of stars and the cluster's overall mass. The universal pattern provides a cosmic census tool. Stars within the same cluster didn't just form together in space. They also formed together in time from the same raw materials. This shared origin creates remarkable similarities between cluster members that persist throughout their lifetimes. Cluster stars have essentially identical ages. While individual stellar ages are difficult to measure, cluster ages can be determined precisely by studying the group as a whole. All members began nuclear burning within a few million years of each other. They also share the same chemical composition. The gas cloud that formed the cluster had uniform chemical makeup throughout. All resulting stars inherited this same mixture of heavy elements from their common birth material. These shared characteristics allow astronomers to study stellar evolution in detail. By examining different cluster members, they can trace how stars of various masses evolve over time while controlling for age and composition effects. What prevents star clusters from immediately flying apart after formation? The answer lies in their mutual gravitational attraction. Every star in the cluster pulls on every other star. These combined gravitational forces bind the group together against disruptive influences. The gravitational binding strength depends on the cluster's total mass and size. More massive clusters with compact configurations maintain stronger gravitational cohesion. Sparse clusters with low total mass remain only weakly bound. External forces constantly try to tear clusters apart. Galactic tidal forces stretch cluster boundaries. Counters with giant molecular clouds disrupt stellar orbits. Stellar evolution removes mass from the system as stars die. Successfully bound clusters survive these disruptions for millions or billions of years. They maintain their structural integrity while traveling through the galactic environment. The strongest clusters persist throughout most of galactic history. Not all stellar groups form tightly bound clusters. Some create loose associations where massive hot stars cluster together without strong gravitational ties. Astronomers call these structures OB associations after the spectral types of their most prominent members. OB associations contain the galaxy's most massive and luminous stars. These stellar giants shine with the power of millions of suns. They emit intense ultraviolet radiation that ionizes surrounding gas across vast regions of space. The associations remain only weakly bound by gravity. Their member stars share common motion through space, but will eventually drift apart over tens of millions of years. They represent temporary gatherings rather than permanent stellar families. Understanding OB associations reveals how the most massive stars influence their galactic neighborhoods. These stellar powerhouses shape the surrounding interstellar medium through their intense radiation and eventual explosive deaths. Some star clusters formed under completely different conditions than modern stellar nurseries. Early in cosmic history, when the universe was denser and more chaotic, special environments created extremely compact spherical star clusters. Astronomers call these ancient structures globular clusters. They contain hundreds of thousands to millions of stars packed into spherical volumes. The stellar density in their cores exceeds anything found in modern star-forming regions. Globular clusters formed when the universe was young and galaxies were still assembling. The extreme conditions of early galactic formation created these dense stellar cities. They represent fossils from a more violent epoch of cosmic history. These ancient clusters orbit our galaxy like stellar satellites. Their extreme age and chemical composition provide windows into conditions that existed billions of years ago when the Milky Way was young and still growing. Star clusters don't remain static throughout their lifetimes. They evolve continuously as their member stars interact gravitationally and the external galactic environment affects their structure. Most clusters gradually expand and lose stars over millions of years. The evolution process removes the lowest mass stars first. These objects have the weakest gravitational attachment to the cluster. Random stellar encounters occasionally accelerate low-mass stars beyond escape velocity. Stellar evolution also changes cluster properties over time. Massive stars exhaust their nuclear fuel quickly and explode as supernovas. This removes mass from the system and weakens the overall gravitational binding. Eventually, most star clusters dissolve completely into the galactic stellar population. Only the most massive and compact clusters survive for billions of years. The majority disperse their stars throughout the galaxy within relatively short timeframes. Stars forming in clusters don't usually end up as isolated single objects. The crowded environment and complex gravitational interactions during formation create an unusually high frequency of binary and multiple star systems. Binary stars consist of two stars orbiting around their common center of mass. Multiple star systems contain 3, 4, or even more stars bound together gravitationally. These complex arrangements form naturally during the chaotic cluster birth process. The binary fraction in young star clusters significantly exceeds that of field stars in the galaxy. Close encounters between forming protostars create gravitational captures and orbital arrangements. The dense cluster environment facilitates these interactions. Understanding multiple star formation helps explain the complexity of stellar systems throughout the galaxy. Many of the stars we observe today were born as parts of binary or multiple systems during their cluster formation epochs. Star formation doesn't only produce objects massive enough to ignite nuclear fusion. The same process also creates smaller objects that fall short of the mass threshold required for sustained hydrogen burning. Astronomers call these failed stars brown dwarfs. Brown dwarfs occupy the mass range between planets and true stars. They contain more mass than even the largest planets, but less than the smallest hydrogen-burning stars. Their cores never reach the temperatures necessary for nuclear fusion. These objects form through the same gravitational collapse process that creates normal stars. They simply happen to accumulate insufficient mass during the formation process. The final mass depends on local conditions in the star-forming environment. Brown dwarfs provide important clues about the star formation process. Their existence demonstrates that stellar birth produces a continuous range of object masses rather than discrete categories. They represent the low-mass tail of the stellar mass distribution. Where do new molecular clouds come from? The answer reveals one of the universe's most elegant recycling systems. Old stars create the conditions for new molecular clouds through their deaths and stellar winds. These processes carve out huge cavities in space that eventually refill with fresh star-forming material. Massive stars and supernova explosions blow enormous bubbles in the interstellar medium. These expanding shock waves push gas outward and create vast empty regions. The hot ionized gas in these cavities gradually cools over millions of years. As the gas cools, it begins to condense and form molecules. Dust grains nucleate from heavy elements produced by previous stellar generations. The cooling process transforms hot empty space back into cold dense molecular cloud material. This cycle ensures continuous molecular cloud formation throughout galactic history. Each generation of stellar death creates the conditions necessary for the next generation of star-forming regions to develop and flourish. How long do molecular clouds survive once they form? The answer depends on when star formation begins within them. Most molecular clouds exist for roughly 10 to 30 million years before stellar birth destroys their structure completely. This lifespan represents a cosmic balancing act between cloud formation and destruction processes. Clouds need time to accumulate sufficient mass and achieve the cold, dense conditions required for star formation. But once stars form, their feedback quickly disperses the remaining material. Scientists measure cloud ages by studying their structure and star formation activity. Young clouds appear smooth and uniform. Older clouds show signs of internal compression and developing stellar nurseries. The most mature clouds contain active star formation that heralds their approaching destruction. Understanding cloud lifetimes helps explain the observed number of molecular clouds in our galaxy. The balance between formation and destruction rates determines how many star-forming regions exist at any given time. Do molecular clouds convert most of their material into stars? Absolutely not. The star formation process proves remarkably inefficient. Only about 2 to 10% of a cloud's original mass ends up incorporated into stellar objects. This low efficiency surprises many people who assume star formation should consume most available material. Instead, stellar feedback processes remove the majority of gas before it can contribute to star formation. The remaining material disperses back into interstellar space. Stellar winds, radiation pressure, and supernova explosions drive away the unconverted gas. These feedback mechanisms act like cosmic vacuum cleaners, removing material from star-forming regions. They halt the star formation process long before completion. The inefficiency explains why molecular clouds disappear quickly once star formation begins. Most of their material returns to the interstellar medium rather than becoming permanently locked up in stellar objects. What ultimately destroys molecular clouds? The very stars they create become their destroyers. Newborn massive stars immediately begin attacking their birth environment through multiple feedback processes that rapidly break apart the surrounding gas structure. Hot stellar surfaces emit intense ultraviolet radiation that ionizes and heats the surrounding gas. Stellar winds blow material away at high speeds. The most massive stars eventually explode as supernovas that completely shatter any remaining cloud structure. These feedback effects do not operate individually. They work together in a coordinated assault on the molecular cloud. Radiation heating weakens gravitational binding. Stellar winds remove heated material. Supernova explosions provide the final devastating blow. The feedback process typically requires only a few million years to destroy even the largest molecular clouds. This rapid destruction timeline explains why star formation occurs in brief bursts rather than sustained long-term episodes. Does the gas dispersed from molecular clouds disappear forever? Not at all. It begins a long journey through interstellar space that eventually leads back to new molecular cloud formation. The dispersed material carries with it the heavy elements forged by previous stellar generations. The hot dispersed gas initially expands rapidly through the galactic disk. Supernova shock waves accelerate it to high speeds that carry it far from the original star-forming region. The gas becomes part of the hot interstellar medium that fills space between molecular clouds. Over millions of years, this hot gas gradually cools and settles back toward the galactic disk. Cooling processes remove thermal energy and allow the gas to condense. Heavy elements within the gas facilitate more efficient cooling than pure hydrogen. Eventually, the cooled gas accumulates into new molecular cloud complexes. These second-generation clouds inherit the chemical enrichment produced by previous stellar generations. The recycling process connects stellar death to future stellar birth across cosmic time. How did the universe acquire elements heavier than hydrogen and helium? The answer lies in stellar nuclear fusion and the explosive deaths of massive stars. Each generation of stars adds newly created heavy elements to the galaxy's chemical inventory. Nuclear fusion inside stellar cores transforms hydrogen into helium and heavier elements. The most massive stars create elements as heavy as iron through fusion reactions. Supernova explosions forge even heavier elements through rapid neutron capture processes. Stellar winds and supernova explosions distribute these newly created elements throughout the interstellar medium. The enriched material eventually becomes incorporated into new molecular clouds, and the next generation of stars that form from them. This chemical enrichment process has operated throughout cosmic history. Early stars contained almost no heavy elements. Modern stars like our Sun contain significant amounts of carbon, oxygen, silicon, iron, and other heavy elements produced by previous stellar generations. Why does star formation occur in organized patterns across spiral galaxies? The answer involves large-scale galactic dynamics that create periodic compression events as gas orbits through spiral density waves. Spiral arms represent regions of enhanced stellar and gas density that rotate more slowly than individual stellar orbits. As gas clouds travel around the galaxy, they periodically encounter these spiral density enhancements. The increased gravitational field compresses the gas. This compression triggers star formation bursts as gas clouds pass through spiral arm regions. Between spiral arm encounters, star formation activity decreases as clouds drift through less dense interarm regions. The pattern creates waves of stellar birth that propagate around the galaxy. Understanding spiral arm dynamics explains the organized structure of star formation in spiral galaxies. The density wave mechanism connects galactic rotation to the detailed patterns of molecular cloud formation and stellar birth throughout cosmic time. Do molecular clouds simply respond to galactic conditions, or do they actually influence galaxy evolution? The answer is both. Molecular cloud star formation drives many of the processes that determine galactic structure and evolution over cosmic time. Star formation releases enormous amounts of energy through stellar winds and supernova explosions. This energy input drives galactic-scale gas flows that redistribute material throughout the galaxy. The feedback creates the hot gaseous halos observed around galaxies. Different star formation rates produce galaxies with different structures and properties. High star formation rates can create irregular galaxies with disturbed morphologies. Lower rates allow the development of stable spiral structures like our Milky Way. The chemical enrichment from stellar nucleosynthesis also influences galaxy evolution. Heavy element production affects the cooling properties of gas and the formation efficiency of subsequent stellar generations. Molecular cloud activity thus drives both structural and chemical galaxy evolution. When did molecular cloud formation first become possible in cosmic history? The answer requires understanding how universal expansion and cooling created the necessary conditions for molecular formation and stellar birth. Early in cosmic history, the universe remained too hot for molecules to survive. Intense radiation broke apart any molecular bonds that might form. Only after several 100 million years of expansion and cooling could stable molecular clouds develop. The first molecular clouds formed from almost pure hydrogen and helium gas. They lacked the heavy elements that facilitate efficient cooling in modern clouds. This made star formation more difficult and less efficient than today. Over cosmic time, successive generations of star formation have enriched the universe with heavy elements. Modern molecular clouds benefit from this chemical evolution and can achieve much colder temperatures and higher densities than their ancient predecessors. Is molecular cloud star formation unique to our galaxy, or does it operate universally throughout the cosmos? Observations of external galaxies provide clear evidence that similar processes operate across many galaxy types and cosmic environments. Radio telescope surveys detect carbon monoxide emission from molecular clouds in galaxies throughout the observable universe. These observations reveal that many galaxies contain molecular cloud populations that share broad similarities. The relationship between molecular gas content and star formation rate remains remarkably consistent across different galactic environments. This suggests that the same physical processes governing molecular cloud evolution operate widely throughout cosmic space and time. Understanding this broad pattern confirms that the molecular cloud star formation cycle represents a fundamental aspect of cosmic evolution. The processes we observe in our galaxy provide insights into star formation throughout the observable universe. What does the future hold for molecular cloud formation and star formation in our galaxy? Current trends suggest that star formation will gradually decline as the available gas supply becomes exhausted over cosmic time. Our galaxy currently converts about 1 solar mass of gas into stars each year. At this rate, the existing molecular cloud material will support continued star formation for several billion more years. But the supply is not infinite. Gas accretion from intergalactic space may replenish some of the depleted material. However, the infall rate appears insufficient to maintain current star formation levels indefinitely. The galaxy faces gradual starvation as molecular cloud formation materials become scarce. Eventually, our galaxy will transition to a predominantly stellar population with minimal ongoing star formation. The molecular cloud era represents a temporary but crucial phase in galactic evolution that transforms primordial gas into the stellar systems we observe today.